Okay. So the next topic after heat transfer is we are studying kinetic theory of gases. So what is meant by kinetic theory of gases? Let us see. So in chemistry also we have studied, no? So in physics we will go in more detail about this kinetic theory of gases. So study of gases at molecular level. Okay, ma? So it means we take every single molecule and we study its characteristics. Understood, ma? So study of gas in molecular level is called as kinetic theory of gases. Okay, ma? So pressure, volume, temperature, kinetic energy are the factors we study in kinetic theory of gases. So these are the terms which we will study. Pressure of the gas, volume of the gas, temperature of the gas, and what is the kinetic energy of each molecule of a gas, or what is the kinetic energy of 1 mole of gas. These are the points which we study. Clear, Nama? So pressure and volume are because of motion of gas molecules. Are you able to understand, ma? So a gas exerts pressure and a gas has volume because of what? Only because of motion of the gas molecules. Clear, ma? So gas molecules, they are moving and they will exert a pressure on the walls of the container. Clear? See here. For example, if this is a container in which a gas is filled. Okay, ma? So these gas molecules, they will be continuously in motion, no, ma? So these molecules, they go and strike the walls of this container. Okay? They go and strike the walls of the container. So it means they are giving some force on the walls of this container, no, ma? So force per unit area is called what? Force per unit area is called as pressure. So pressure of the gas is only because of movement of the gas molecules. If gas molecules doesn't move, there is no concept of pressure. Understood, no? Similarly, volume of the gas is only because of motion of the gas molecules. So gas molecules, they have a tendency, no? So whatever volume they find, they try to cover the total volume. Okay? So volume of the gas is also existing only because of motion of gas molecules. Another point is that, clear, ma? Motion of gas molecules is because of what? Is due to, okay, ma? Temperature of gas. Okay, ma? So pressure and volume, they are because of motion. Motion is due to what? Motion of the gas is only because of temperature of the gas. Okay, ma? Because gas molecules, they have some temperature, they have some kinetic energy. Clear, Nama? So what is the next point I can write? Temperature is because of kinetic energy of gas molecules. Clear? So molecules continuously, they are in random motion, Nama? So because of what is the reason for that motion? Kinetic energy of the gas molecules is the reason, because they have some velocity. And who gave this velocity to the gas molecules? Who gave this velocity to the gas molecules? Velocity and kinetic energy are because of heat energy present in them. Okay, ma? So these molecules, they are in continuous motion because of what? Because of the energy they have. Clear? And that heat energy converted into kinetic energy. Because kinetic energy has increased, temperature of the gas molecules has increased. Because temperature of the gas molecules have increased, that is why they are able to move. Are you able to understand, ma? And motion causes pressure and volume of the gas. Okay? So therefore, if I start cooling a gas, what happens, ma? Can you say? If we start cooling a gas, that is, if I reduce the temperature of the gas, what happens? Reducing the temperature means what actually? Removing heat energy, no? Removing heat energy from the gas molecules. So if heat energy is removed, what happens to the temperature? Reduces. Temperature reduces means kinetic energy reduces. Kinetic energy reduces means the pressure exerted by the gas also reduces. So this is what happens. Clear, Nama? So if we start cooling a gas, then it means what we are doing, it means we are removing heat energy. Okay? And if we remove heat energy, what happens to temperature? Temperature of gas reduces. Okay, ma? Therefore, kinetic energy also reduces. So, pressure of the gas also reduces. So, these are the relations between different factors of gas. Are you able to understand, ma? So, gases are exerting pressure only because of kinetic energy they have. Kinetic energy is only because of temperature. Temperature is because of energy of the gas molecules. Clear, no? Okay. Now, if I heat the gas up to minus 273.15 degrees Celsius, then can you say what will happen? Okay, ma? Similarly, if we cool the gas up to minus 273.15 degrees Celsius, then at a particular temperature, gas solidifies. Okay, ma? It takes the solid form, and at minus 273.15, the internal energy of system completely becomes zero. Okay, ma? So this is what happens if I start cooling a gas. If I start cooling, at some point this gas converts into solid form, nama. First it converts into liquid form, then it converts into solid form. And even it has converted into solid form, it can have energy, because molecules, they will be vibrating, no? If I take the molecules of this pen, they will be vibrating around their mean position. Clear, no? So even if I reduce the temperature to minus 273.15, then the total vibrational energy, rotational energy, every energy will become zero. It means total internal energy will completely become zero. Understood, Nama? That's it. So that is the reason for pressure and volume of a gas. Okay? Then we know what is meant by Avogadro number, Nama? Avogadro number. What is meant by Avogadro number? Na is equals to 6.023 into 10 power 23 atoms or molecules, ions, anything. Clear, number? So therefore, 1 mole is nothing but Avogadro number. Clear, number? Molar mass. Mass of 1 mole of any particles. It may be atoms also, molecules also, ions also, or anything. Clear, number? Molar mass is also called as molecular weight. Or if they are atoms, they can be called as atomic weight. Okay, ma? So like this, you can call them as molecular mass also. Okay? There are many names for 1 mole of a gas. Are you able to understand, Noma? That's it. So therefore, if I take the mass of single oxygen atom, okay. So if I take mass of 1 oxygen atom. Then how much it is? It is equals to 16 atomic mass units. Okay, ma? Single oxygen, only 1 oxygen atom, molecule I am not taking, atom. Then its mass will be 16 atomic mass units. Similarly, mass of oxygen molecule is how much? It is 16 2s are 32 AMU. Background music, right? Okay, ma? So similarly, if I take mass of Avogadro number of molecules, okay, ma? Oxygen molecules, then what can I do? I can write it as 6.023 into 10 power 23 multiplied by, what is the mass of each one? It is 32 AMU. Clear, no, ma? Are you able to understand what is happening? Mass of single oxygen molecule is 32 AMU. I want to calculate the mass of 1 mole of oxygen molecules. 1 mole means this many number, no? So multiply this number with mass of single oxygen molecule. Therefore, it converts into what? It converts into 32 grams. Clear, no, ma? Are you able to understand? So, if atomic mass, if you take AMU, if you take in terms of AMU, it means we are taking single molecule or single atom. But the same if you take in terms of grams, then it means that you are measuring that one in terms of moles, number of moles of a gas. Is it clear? Make a note. Background music and okay, ma? So therefore what I can write, okay, ma? Brahmandanga record avutadi, anduku record avunu. Okay, ma? So if mass is taken in AMU, it means we are talking about single atom or single molecule. Single atom or single molecule. Understood, no, ma? But if mass is taken, in grams, then we are dealing in mole of molecules. Okay, ma? So it may be 1 mole, 2 mole, half mole, 0.5 moles, anything. Okay? If we are talking in terms of moles, it means we are dealing in grams. If we are dealing in AMU, it means we are talking about single atom or single molecule. Okay, ma? So this is one point which you should remember. Okay? So then we study about ideal gases. Okay, ma? Ideal gases. So ideal gases doesn't exist. Ideal gases does not exist. But for real gas, if I take real gases, and if their temperatures are very high, and pressures are very low, then what happens? Then real gases, or just I can say they behave like ideal gases. Are you able to understand, ma? So ideal gases doesn't exist in the universe. That's what we have been saying, no, ma? Okay, but we are doing every calculation by taking ideal gas only. So but real gases, if temperatures are very high and pressures are very low, then they behave like ideal gases. This proof also we have studied in states of matter, no? So that's it. Now let us see what are the properties of ideal gases. Okay, ma? So, properties of ideal gases. Okay, ma? Atoms or molecules are perfect spheres. Okay, ma? So in ideal gases, we consider them to be perfect spheres. But volume of molecules is considered 0. Volume is considered 0. Okay? It means they behave like, or they are considered point masses. Okay, ma? So all the molecules of ideal gases, we are considering their volume to be very small. So we consider them to be point masses. In real gas equation, we have written one correction term for volume number, that is for real gases. But for ideal gases, we consider they don't have any volume because they are very, very, very point masses when compared to the volume of the cylinder. Understood, Nama? And the collisions between them is considered elastic. Okay, ma? Collisions between them is considered to be elastic collision, perfectly elastic collision. Clear? Similarly, the forces of attraction or repulsion between them is considered 0. Okay, ma? So, forces of attraction or repulsion between molecules or atoms is considered how much, ma? It is considered 0. Okay? So these are some of the properties of ideal gases. Though there are some more properties which we doesn't require. Up to the requirement of our topic, these points we are supposed to remember. Understood, Nama? That's it. Sima. So we are trying to derive an equation for pressure exerted by the gas on the walls of a container. Okay? Sima. So consider this is a container in which many molecules of gas are present, ma? And we are taking one gas molecule whose mass is m, and along x-axis it is traveling with a velocity of vx. So this molecule can have any velocity, no, it will have velocity along x-axis also, y-axis also, as well as z-axis also. We are taking one velocity along x-axis, so that it goes and strikes with the walls of the container, wall of this container. Okay, ma? So total velocity, how I can write? V dash is equals to Vxi cap plus Vyj cap plus Vz k cap. I can call this velocity as RMS velocity. Are you able to understand? So if I take the magnitude, this is how I have to take magnitude of a vector, no, ma? So V RMS is equals to square root of Vx square plus Vy square plus Vz square. Okay. Now, first of all, we will consider velocity only along x-axis. I will take Vx. So therefore, now what is the momentum in this direction? Momentum in this direction is mass into Vx. This is the momentum in this direction, Nama. Momentum mass into velocity. Okay, Nama. So this goes and strikes with the walls of the container. Then it will return back with how much velocity? It will return back with same velocity, because already we have considered that these molecules, they are performing elastic collisions, Nama, because we are considering ideal gases. And every ideal gas will have elastic collision. Elastic collision means what is the velocity with which they are striking? They will return back with same velocity. Okay. But in returning back, this velocity I have to take a negative velocity, no? I have to take a minus Vx velocity. Okay. So therefore, what is the momentum while returning back? Momentum while returning back is minus m into Vx. This is what I can write now. Momentum is a vector quantity, no? In one direction I have taken positive, another direction it will become negative. So what is the total change in momentum? Change in momentum is P final minus P initial, or P initial minus P final, anything we can write. Are you able to understand, ma? So mvx minus mvx will become 2 mvx. Are you able to understand? So this is the change in momentum. So only we are taking magnitude, ma. Okay. So change in momentum is how much? 2 mvx. Why we are changing momentum? Because I want to force, no? What is the formula of force according to Newton's second law? F is equal to dp by dt. Rate of change of momentum of a body is directly proportional to force. That is Newton's second law, no? So change in momentum is 2 mvx. And time taken. What is the time taken? I want a time taken between two collisions. Time taken between two collisions. Sima. So first of all, this molecule collides here. Okay. Then it goes to other end of the wall. No? Here one more collision happens. Then again it returns back. It means again to return to the same position, it has to travel 1 L distance, and in returning also it has to travel one more L distance. So total distance traveled is how much? 2L. To collide at the same position, it has to travel 2 times, no? First it should go to one end of container and return back also. Clear, no? So therefore, time taken between two collisions is 2L divided by velocity along x-axis. Clear? So therefore, change in momentum divided by change in time is called as force. So this is the calculation which I have done. So this is the force applied by each gas molecule. Every single gas molecule, it will exert this much of force on the walls of the container. Are you able to understand, ma? Okay. So, but how many molecules will strike per second? There may be many molecules, no? So in the gas, there are many molecules. So many molecules, they go and strike the wall of the container. So therefore, what is the pressure exerted by n molecules? Just you multiplied this force by n. So mn vx square divided by L. And what is this force? This is force exerted by n molecules. Are you able to understand what is happening? Force exerted by n molecules is called as Fn. Okay. Now pressure formula, force per unit area. So this wall will have an area of A, length into breadth. Wall will have an area of A. So force divided by area will give pressure. In denominator here I have L, no? L means what? The distance traveled by the what you call this container. Nothing but length of the container. Are you able to understand? Length multiplied by area of cross section will give what? It will give volume of the container. Are you able to understand, Amma? So therefore, I got relation up to here. Now see. So now I know Vrms square is equals to square root of Vx square plus Vy square plus Vz square. But I take all the velocities, they are equal. It means velocity along x-axis, velocity along y-axis, and velocity of z-axis. Everything I will take to be same. So therefore, Vrms, how I can write? Because velocities are same. Instead of Vy and Vz also, I can write Vx only, no? So therefore, it will become 3Vx square. Therefore, what is RMS Vx here? Vx square is equals to RMS velocity square divided by 3. So here instead of Vx square, I will write Vrms square divided by 3. Then this is my final equation to calculate pressure exerted by gas on the walls of the container. Okay, ma? So because of kinetic energy only, gas has pressure, ma. Pressure means what? Just the force with which the gas is striking the walls of the container is called as pressure. Is it clear? Make a note up to here. So very important equation, ma. Many times questions were given on this relation, and questions were given on calculation part also. That's why I said you the calculation also. So questions will be asked on calculation of pressure also. Understand? Make a note. Let us see this question. So in a period of 1 second, so 5 into 10 power 23 nitrogen molecules strike a wall which is having an area. So these are nitrogen molecules, ma. So these nitrogen molecules, they are striking the walls of this container. So area is given. So assume that molecules move with a speed of 300 meters per second and strike a head-on collision. What is the pressure exerted? Pressure is nothing but force per unit area, no, ma. Force is nothing but dp by dt, no, divided by A. Clear, no? And what is dp? dp is nothing but change in momentum. mv minus of minus mv. Already we have done this one, no? So how much it is? 2 mv. Okay? 1 minute. So see. So this is 2 MV number, 2 times the change in momentum. Okay. Time taken how much? 1 second. In 1 second, these many molecules are striking. So dt is nothing but 1 second. So 2 MV is how much? 2 into, what is the mass of each single molecule? Mass of each nitrogen molecule is 4.65 into 10 power minus 26 multiplied by, and what is the velocity of each molecule? Velocity is 300. That's all, Nama. Okay. So this is the change in momentum. This is the change in time. Area is already given. No, what is the area? 8 centimeters square. Okay, ma. So area is equal to 8 into 10 power minus 4 meters square. Clear? That's all. Just substitute all these values. That is the required pressure. That's it. Okay, ma. So do this total calculation. So the pressure which you should get is 17.4 kilopascal. 14 or 17? 17.4. 17.4 kilopascal. Newton per meter square and Pascal both are same. Clear? That's it. Okay, Sima. One mistake which we have done here is we have calculated pressure because of only one single molecule. Huh? I want to calculate pressure of these many molecules, no? So therefore multiply them with the total pressure. So therefore P total. Total pressure is how much? What are the number of molecules, ma? So 5 into 10 power 23 multiplied by pressure exerted by each molecule. Okay. And pressure exerted by each molecule, this is the relation. So therefore it is 5 into 10 power 23 multiplied by dP. What is the dP value? Change in momentum is 2 into 4.65 into 10 power minus 26 divided by dt. Time taken is 1 second multiplied by area is 8 into 10 power minus 4. That's it. If you do this calculation, then you will get 17.4 kilopascal. 300 we did not put into 300. That's it. Okay. That's the pressure exerted by the nitrogen gas molecules.